Hi children, today I'm going to start my discussion on dielectrics and polarization. The topic that I'm discussing today is dielectrics. Dielectrics. Yes. What are dielectrics? You already learned about what is called a dielectric constant. So my first question is, what are dielectrics? If you open your NCERT book and the topic dielectrics, you will see the first sentence under it, under the heading dielectrics. Dielectrics are non-conducting substances. What are dielectrics? Dielectrics are non-conducting substances. Dielectrics are non-conducting substances that transfer electrical effects by a mode called electric displacement. The mode involved is what is called electric displacement. The mode of transfer of electricity that is involved in dielectrics is called electric displacement. Before we deal much into dielectrics, we have to see what are the types of dielectrics. Dielectrics are basically of two types. One is called polar dielectrics. The second category is called non-polar dielectrics. Then what are polar dielectrics? Polar dielectrics are dielectrics whose molecules have a permanent dipole moment. The molecules of a polar dielectrics have a permanent dipole moment. The molecules of a polar dielectric has got a permanent dipole moment. That means in case of a polar molecule, the centers of the positive and negative charges are separated by a small distance. In case of a polar dielectric, the centers of the positive and negative charges are separated by a small distance. Some examples for polar dielectrics are HCl, H2O. Some examples. Then what is going to be non-polar dielectrics? Obviously I can say only one word. I have to say no permanent dipole moment. The molecules of a non-polar dielectric has got no permanent dipole moment or no intrinsic dipole moment. The molecules of a non-polar dielectric has got no permanent dipole moment, or in simple, no intrinsic dipole moment. Some examples of such molecules are H2O2. Then what is the orientation of a non-polar dielectric? You can easily say in case of polar, the centers of the positive and negative charges are separated by a small distance. When it comes to non-polar, come on, tell me, what is that going to be? The centers of the positive and negative charges must be coinciding. The centers of the positive and negative charges must be coinciding in case of a non-polar dielectric, and therefore the molecules of a non-polar dielectric have no permanent dipole moment. Molecules of a non-polar dielectrics have no permanent dipole moment. When it comes to polar dielectrics, the molecules have a permanent dipole moment. This is the first idea you have to understand regarding the types of dielectrics, polar and non-polar. Now let us see the behavior of non-polar dielectrics. Non-polar dielectrics. Now before I discuss this, please bear in mind that polar dielectrics are dielectrics which has a molecular dipole moment, and there is no molecular dipole moment. In case of polar dielectrics, the positive and negative charges have a separation. In the case of non-polar dielectrics, the molecules does not possess any separation. That is what I will say. It is in the molecular level. Dipole moment is defined at the molecular level. This is very, very important. You have to understand this discussion. Now let us see about the behavior of non-polar dielectrics. Okay, let me take a block of a non-polar dielectrics. Although I say block, you have to see that it's a small volume. In a small volume, there will be many number of molecules, right? In a small volume, you will find many number of molecules. So let me consider in the case of a non-polar dielectrics. In the absence of an external field, so here I say E is equal to 0. Now see, in this case, the centers of the positive and negative charges are coinciding. Centers of positive and negative charges are coinciding. Positive, negative, positive, negative, positive, negative. So because there is an external field, so they are coinciding. Now what will happen if such a molecule is placed or such a dielectric is placed in an external field? So I am saying this is a positively charged plate, this is a negatively charged plate, and I am placing this dielectric in the presence of an external field. And what is the direction of this electric field? Come on, tell me. What is the direction of this electric field? It is from positive to negative. Is it no? The direction of the electric field is from positive to negative. So let's check it. What will happen then? Obviously, you can answer. As there is a positive charge here, there is a possibility that negative charges will be pushed towards this side. Electric field, right? There is an electric field, and negative charges always experience a force in the direction opposite to the field. So negative charges are accumulated here, positive charges are accumulated here. Now tell me, is there any dipole moment here? Is there any dipole moment existing here? There is a negative charge, there is a positive charge. Now they are separated by a small distance. I should say there is a dipole moment. And what is the direction of the dipole moment from? Direction of dipole moment from negative to positive. Now see, in the presence of an external field, in the presence of E, external field. So here the external electric field is equal to 0. External electric field is 0 here. It is not 0 in this case. This is negative, this is positive. Now let us consider another molecule again, negative, again positive, and take the next molecule, negative, positive, negative, positive, negative, positive, negative, positive. You can see that there is a dipole moment here. What is the direction of this dipole moment? From negative to positive. What is the direction of dipole moment here? Again from negative to positive. What is the direction of dipole moment here? From negative to positive. What is the direction of dipole moment here? Again from negative to positive. What is the direction of dipole moment here? It's again from negative to positive. What is the direction of dipole moment here? It is again from negative to positive. That means when a non-polar dielectric is placed in an external field, when a non-polar dielectric is placed in an external field, and a non-polar dielectric is placed in an external field, a dipole moment is induced in this material. A net dipole moment is induced in this material from negative to positive, right? That is in the direction of, from negative to positive inside this molecule. That is in the direction of the external field, right? This is the direction of the external field. The direction of the external field is likewise, and this is the direction of the dipole moment. And so now we will conclude what? When a non-polar dielectric is placed in an external field, a dipole moment is induced in this material in the direction of the external field. A net dipole moment is induced in the direction of the external field. This is the behavior. Now the question I would like to ask you is, what will be the direction of, what will be the strength of this dipole moment depend on? The strength of this dipole moment depends on strength of net dipole moment. Is directly proportional to the applied external field. The strength of the external net dipole moment depends on the strength of the external field. If it is directly proportional to the strength of the external field, this is called a linear isotropic. Such dielectrics are called a linear isotropic dielectrics. Okay, such dielectrics are called linear isotropic dielectrics We will discuss about later after considering the behavior of polar dielectrics also. Okay, let us take the next idea. Polar dielectrics. So what are polar dielectrics again? These are dielectrics whose molecules have a permanent dipole moment. Okay, let us consider such a small volume of a polar dielectric here. Tongue twister. Okay. So let us consider the situation in the absence of an external field. Then what are polar dielectrics? Dielectrics whose molecules have a permanent dipole moment. Okay, so I am taking the first molecule. This is negative, this is positive. They are separated by some distance. And here the direction of dipole moment is in this direction. Molecular dipole moment exists in the case of a polar dielectric. Now take another molecule. I am taking this one. Negative charge here, positive charge here. Now take another one. Negative charge here, positive charge here. Take another one. Positive charge here, negative charge here. Take another one. Negative charge here, positive charge here. That means in the absence of an external field, there are individual dipoles, but what is the effective dipole moment? As you see, this dipole moment is in this direction, 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 this dipole moment is in this direction. The individual dipoles are randomly oriented. They are randomly oriented. Individual dipoles are randomly oriented. Now question, what is the cause of this random orientation? Cause of this random orientation. I would say the cause of the random orientation is thermal effects. As we have seen in every case, as temperature increases, randomness increases. The same case is also coming here. Thermal agitation effects, it is what exactly said. Thermal agitation effects. When external, so in the absence of the thermal effects, this would have oriented in the same direction, giving rise to a net dipole moment. But due to these thermal effects, the dipoles are randomly oriented, giving rise to a negligible dipole moment or zero dipole moment in the absence of an external field. The situation is similar. Okay, what I can say is that a similar example with our class. When a teacher is absent in your class, what will you do? You tend to align in different directions, don't you? You tend to align in different directions when a teacher is not present in the class. One will be looking at that side, another will be looking in that side, someone will be looking for the arrival of the teacher. So you'll be oriented in random directions. So now one can say the cause of that is thermal effects. Very hot inside the class, that is the reason why you are all sitting in random directions. Right? Just fun only. Now let us see the situation. In the presence of an external field, what happens in the presence of an external electric field? E external not equal to 0. So this is positively charged, this is negatively charged. I'm sure that you will say, yeah, fine, okay, if you take all these molecules, they are going to align in this there. This is negative, positive, negative, positive, negative, positive. Okay, you will say this will happen. Will it exactly happen? Now again think about your situation. Will it happen? Okay, let's take our class itself. Teacher was absent. Now a teacher comes to the class. Can you assure that you will all sit in the same orientation rigidly such that you are all concentrating to the teacher properly? Answer is a big no. Why? That depends on the teacher, right? If the teacher is so rigid, you will sit according to what is instructed by the teacher. But if the teacher is liberal, still, I don't think this orientation would happen. Then what will happen? One dielectric will be oriented like this. One molecule will be oriented like this. Another molecule may be oriented like this. Another molecule will be oriented like this. Some another will be likewise. Okay, I'm saying some another will be likewise. Some will be oriented likewise. What I can say altogether is that there is a net dipole moment, right? There is a dipole moment in this direction, and this will have a dipole moment, but still it has got a component in this direction, right? I can altogether what I can say is that a net dipole moment is induced in the direction of the external field. A net dipole moment is induced in the direction of the external field. Net dipole moment is induced in the direction of the external field. The same way, likewise, we have seen with a non-polar dielectric. In the case of a polar dielectric also, a net dipole moment is induced in this direction. Now the question again, why is it likewise? Maybe you find a little difference from the figure drawn in the NCERT book, that doesn't matter. Because what I want to say is that a net in the presence of an external field, whatever be the strength of the external field, a net dipole moment is induced in the direction of the external field. A net dipole moment is induced in the direction of the external field. Okay, agree to that. Now, what is the strength? That is a direction. I said the direction of the don't misinterpret my words. I said only that a net dipole moment is induced in the direction of the external field. The direction of the induced dipole moment is in the direction of the external field. Now, on what factor does the magnitude of this dipole moment? On what factor the magnitude of the dipole moment depends? That is where I said, if the teacher is liberal, still many will be sitting in different directions. But if the teacher is somewhat strict, more students will be orienting in the direction proposed by the teacher. If the teacher is more strict, more students will be orienting in the direction proposed by the teacher. If it is a very strict teacher, then what will happen? Everyone will sit likewise, right? Everyone is going to sit likewise, because we are so afraid of that teacher. I won't specify that who is that teacher. You can find examples in your classrooms or in your localities or in your knowledge, whatever it be, sorry. What I'm saying is that the strength of the induced dipole moment is a measure of this external electric field. Strength of the induced dipole moment is a measure of the external electric field. The same I said with a non-polar dielectric also. But in case of a non-polar dielectrics, the molecules does not have a permanent dipole moment. But in case of a polar dielectrics, the molecules have a permanent dipole moment. The reason is that thermal effects are randomly orienting it. Then the question I would like to ask you, what is the role of this external electric field? What is the role of this external electric field? What is the importance of this external electric field here? As you can see from these two figures, the significance of external electric field is in orienting these dipoles, right? The significance of this electric field is to orient these dipoles in the direction of the external field by overcoming or by fighting against, I would say fighting against the thermal agitation effects. By fighting against the thermal agitation effects, so that means the electric field is making a fight against the external electric field in order to orient the dipoles in favor of the external field. That is where I say, if the strength of the electric field is more, it will have more fighting power. It will have more fighting power. It will fight more such that it will orient the dipoles in the direction of the external field. Right? So some work has to be done. When I do fight against someone, I will lose my energy for that fight also. Right? I will lose my energy for that fight. So as electric field is trying to orient these dipoles, electric field will be losing its energy. Against whom? against the thermal agitation effects, and the remaining will be stored as the energy of the configuration. What is that energy? I am not specifying here. You can understand energy associated with the state of configuration. What is that energy called? Think about, get it. So this is the idea I can say regarding the behavior of non-polar dielectrics and polar dielectrics. Now the next thing I'm going to discuss is the behavior of a dielectric. Okay, just seen the behavior. Now let us consider in the presence of an external field. Okay, as I said, this is a positively charged plate, this is a negatively charged plate, and I place a dielectric as a volume, a small volume of the dielectric is placed between this one. Although I say small volume, that volume must contain an enormous number of molecules, right? Molecules are of very small size always, right? Which means that will contain an enormous number. And the direction of the external electric field, let me take it as E0. External electric field is E0, and that is always directed from positive to negative. Now for a regular orientation, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. Since I have drawn a bigger figure, so I need to draw a bigger one also. Okay, tired, so I will reduce to this amount only. Okay, now see this figure. And I'm taking a small volume of this or a certain region here. Now tell me, this is a positive charge, this is a negative charge. This is a positive charge, this is a negative charge. Right? Just a minute. Now you can see that the region which I am shading here, I don't know whether you will be able to see that shading. In the shaded region, I have made a lighter shading only. In the shaded region, you can see this positive charge, this negative charge. This positive charge, this negative charge, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. So what happens here? In a solid, the molecules are very thickly packed. In a solid, the molecules are very thickly packed such that this positive and this negative charges are very close to each other. This positive and this negative are very close to each other. This positive and this negative are very close to each other. These two are very close to each other. This is very close to each other. So on. What will happen? The effect of one positive will be nullified by the effect of another negative. That means otherwise if you consider this, okay, you can see here the effect of one positive will be nullified by the other negative, or they will neutralize each other's effect. Which means I can treat this dipole or dielectric like, yes, see, this is a positive region, this is a negative region, like a set of negative charges placed here. Because this positive, the effect of this positive is nullified by this negative. Similarly, the effect of this positive is nullified by this negative, such that this positive negative cancel, this positive negative cancel, this positive negative cancel, this positive negative cancel, positive negative, positive negative, positive negative, positive negative cancel each other. That means there is a region of negative charge nearer to the positive plate, and there is a region of positive charge near the negative plate. Right? Hope you can see this. Okay, so which means the outside field, if I say E0 is the outside field, the direction of E0 is likewise. And look at the dielectric now. This is a region of positive charge. This is a region of negative charge. Now you can see that these charges are accumulated on the surface because inside the volume this positive and negative charges cancel each other's effect. Which means it is the dielectric is now supposed to be having charges accumulated on its surface, right? This is on the near surface of the dielectric. This is on the far surface of the dielectric. This is on the near surface of the dielectric. This is on the far surface of the dielectric. So dielectric is supposed to have a charge density, which is sigma. That is surface charge density, because now the dielectric is supposed to have a charges located on its surface. This is minus sigma p, I would say, and this is plus sigma p, where sigma p is defined as what is called induced surface charge density. This is induced surface charge density. Sigma p is defined as the induced surface charge density. And now we can see there is an induced electric field. The direction of the electric field, as we all know, it is from positive to negative. There is an induced electric field that is in the direction opposite to the external field. External field is E0. Induced electric field is opposite to the external field. Now let us recollect this. Now, as I said in today's discussion, when a dielectric is placed in an external field, please bear this in mind. When a dielectric is placed in an external field, a dipole moment is induced in the direction of the external field. A dipole moment is induced in the direction of the external field. An electric field is induced in the dipole moment in the direction opposite to the external field. An electric field is induced in the direction opposite to the external field. Now the question I am asking is, what is net field inside a dielectric? The net field inside the dielectric. Net field. What is net field inside the dielectric? You can see it is E0 minus E induced. The net field inside the dielectric is equal to E0 minus E induced. The net field inside a dielectric is E0 minus E induced. The net field inside a dielectric is E0 minus E induced. What is E0? E0 is the applied external field. And what is E induced? Which is the field induced inside a dielectric. Hence, net field inside a dielectric is E0 minus the induced electric field, that is E induced. This is the field inside a dielectric. So this is an important point you have to understand. But we have already learned according to Coulomb's law is that the net field inside a dielectric is E0 divided by K, where K is called the dielectric constant. K is called the dielectric constant, which means I can say E0 divided by K is equal to E0 minus E induced, or the induced field inside a dielectric is E0 minus E0 by K, or that is E0 into 1 minus 1 by K. This is the net field. This is the field induced inside a dielectric. Induced field inside a dielectric, I have to say. Induced field inside a dielectric. Now, this also is an important relation you have to understand. Now, from here, we can arrive at the field induced in the case of a conductor. For a conductor, what is the value of K? K is equal to infinity. Dielectric constant of a conductor is infinity. Then what is going to be 1 by K? 1 by infinity that is 0. So for a conductor, the induced electric field is equal to E0. This is the case I can say for a conductor. For any conductor, the field induced is equal to the external field irrespective of the value V0. For a conductor, whatever field you apply, that much field also will be induced in the conductor, but what about the directions of the two? They will be opposite. In the case of a conductor, the induced electric field is always equal to the applied field. Induced electric field is equal to applied electric field. This is the case I can say this is applicable only for a conductor. For a conductor, the induced electric field is equal to the applied electric field. Applied electric field. The induced electric field is equal to the applied electric field for a conductor. This is an important point you have to understand for a conductor. Okay. Now the question, what is the reason for this? Induced electric field and applied electric field are equal. Answer is very simple. In case of a conductor, the free charge carriers are enormous, which is about 10 raised to 29 per meter cube of the volume. That means if you take 1 meter cube of a conductor, 1 meter cube volume of a conductor, the number of free charge carriers present there is 10 raised to 29. 10 raised to 29 is the number of charge carriers present in the case of a conductor. So this is an important point to bear in mind. For a conductor, the value of K is infinity, which means E induced is equal to E0, where E induced is called induced electric field and E0 is the applied electric field. Now, before we wind up this session, a small portion also remaining, that is dielectric polarization. So what I mean by dielectric polarization, it is also otherwise a polarization vector. Polarization vector capital P is equal to small p induced divided by volume. What is small p here stands for? The dipole moment. Small p is the dipole moment. What do you mean by small p induced? Or I will just write as small p IND. IND stands for induced. Small p induced dipole moment per unit volume. Okay, better is to write in complete form. Induced dipole moment divided by volume, that is small p induced divided by volume. Now consider a dielectric of length L. As I told you, when I placed in an external electric field E0, likewise, negative charges will be induced on the near side, positive charges will be induced on the far side, the farthest side. That means the charges appear on their surface itself, right? Now, let me take the length of the dipole as L. The charge density here is minus sigma p, the charge density here is plus sigma p. Which means I can say the polarization vector P is equal to the charge induced into dipole moment I have to get, right? Dipole moment, that is charge induced into length. That is a formula for the dipole moment, right? So Q induced into L divided by the volume of the dielectric. Let L be this length and cross-sectional area is A. I will write as A into L as the volume. A into L. This is the magnitude of the polarization. Polarization is actually a vector because dipole moment is a vector, right? So I use a vector symbol here, induced dipole moment per unit volume. So the magnitude of the polarization vector is charge induced as a result of the external field into L divided by volume is area of cross section of the conductor into length of the conductor. So I can cancel the two L's here. This is Q induced by A, which is sigma P. The magnitude of the polarization vector is equal to the induced surface charge density This is what I have to say. This can also be written as, which is equal to chi E into E net. Chi E into E net, where chi E is called electric susceptibility. I'm sorry, this is a tongue twisting word. Electric susceptibility, and E is the net external electric field. Net field, not a net external, net field inside the dielectric. This is the relation you have to understand for a linear isotropic dielectric. LID. Linear isotropic dielectric. I will prove this relation in the very next class. The derivation is not important as far as the board examination is concerned, but it is given in our NCERT textbook as a blue column, in a blue column, that is electric displacement. That will be discussed in the next class. The class is lengthy today, but this is a single topic and I was supposed to complete in a single class. That is the reason why. Hope it is clear to you. Study well. Thank you.